Have you ever stopped to ask yourself, what is time really? Is it an endless river carrying everything away, or merely an illusion within our minds? We use it to measure our lives, the evolution of all things, even the birth and death of the universe itself. Humans have always been obsessed with defining, understanding, and most of all, controlling time. And nothing illustrates this obsession more clearly than our burning dream of time travel. From ancient legends of strange journeys through the ages to blockbuster sci-fi movies on the big screen, the idea of jumping through different points in time always sparks our imagination. But is this just a far-fetched dream, or is there a shred of scientific basis behind it? In this video, we won't just skim over dry theories. We'll dive deep into the profound relationship between humanity and time, explore perspectives we haven't thoroughly discussed before, and perhaps you'll find a fresh answer to a millennia-old question. Can we truly travel through time? Let's begin this journey. Please like and subscribe to my channel. Please comment what you want to suggest to me. That will be the motivation for me to make videos every day. Thank you very much. Now let's get back to the topic. Time travel. Does it exist from the perspective of science and physics? 1. Time through the lens of philosophy, a multidimensional concept. To truly understand time, we need to set aside the fantastical images from movies and start from a more solid foundation. That's philosophy, the wellspring of all science. Philosophy helps us realize that time isn't always the same in every instance, and how we perceive or categorize it heavily depends on our individual perspective and the field we're examining. First, let's talk about scientific time. This is the concept of time we're most familiar with, measured by tools like clocks. It's divided into uniform segments, devoid of color or emotion. A second in Hanoi is the same second in New York or on Mars. It's cold, objective, and unaffected by human mood or circumstance. Whether you're in prison or free in the world, time flows steadily, relentlessly, without waiting. It's the succession of all things, entirely external and mechanical. But is that all there is to time? Certainly not. When humans begin to interact with this flow, another type of time emerges: physiological time. This is a type of time influenced by human factors, reflecting the growth and changes within our bodies. Think about a small wound. A wound on a 5-year-old child will heal significantly faster than a wound on a 50-year-old. Why? Because the child's body is in a vigorous growth phase, and cell regeneration happens more quickly. This demonstrates that time isn't just an objective measure, but also possesses a subjective quality, tied to the biology of each individual. Going a step further, we have psychological time. This is time measured by emotions, feelings, and personal impressions. When we're young, time seems to fly by. Every day is a new discovery, an exciting experience, a new relationship. We're swept up in the busy current of society with countless facts and tasks to resolve. But when freedom is taken away, or when we're in a situation of waiting or suffering, time feels infinite. You've probably heard the saying, "A day in prison feels like 1,000 years outside." This is the clearest proof of the subjective nature of psychological time. While these basic concepts of time are important, they're not enough for us to truly grasp and control it. To go deeper, we need to turn to philosophical inquiry, especially Western philosophy, where reflections on time are presented with seriousness and depth. One of the most emblematic figures is Heraclitus, an ancient Greek philosopher who lived around 544 to 483 BCE. Though from an aristocratic family, his life was filled with hardship and solitude. From Heraclitus's perspective, everything in our world is constantly in flux, endlessly moving and changing. The world is like an eternal river. His famous dictum, "No man ever steps in the same river twice" has become a symbol for the continuous transformation of all things. The river always flows, and when you step into it a second time, it's no longer the same water. Even when we think something is stationary, it's actually in a state of transformation. Time is inherently motion, never stillness. However, not everyone agreed with Heraclitus. Parmenides and his student Plato argued for the existence of eternal, unchanging realities beyond the transient world of phenomena. All change, they believed, is merely superficial, not the true essence. Plato believed that alongside the constantly changing world of appearances, there exists a world of ideas, of the soul, an eternal, unchanging world, beyond the confines of time. For them, time was merely the moving image of an unmoving eternity. This perspective opens a door to contemplating existences untouched by time. More than 200 years later, around 300 BCE, we see the emergence of new currents of thought. The philosopher Aristotle noted that the essence of nature is change. He defined the philosophy of nature as the study of changing things, and accordingly, time is the measure of motion, based on the concepts of before and after. Time is continuous because it belongs to continuity, and only the present is truly real. The past is gone, the future hasn't arrived. Only this present moment is where we truly live. Next, a famous philosophical school emerged, Stoicism. This philosophy carries deep meaning about contentment, a quiet, peaceful, and serene life found through self-restraint and self-mastery. For the Stoics, time has no true substance, but all existence and movement happen within time. Time resides within the life of the world, meaning within creation. The wise philosopher Epictetus, a prime representative of this school, taught that we should follow and accept time, living in harmony with creation. This emphasizes the importance of embracing the flow of time rather than trying to resist it. In the latter half of the 17th century, we encounter a formidable intellect, Gottfried Wilhelm Leibniz. He was a polymath who played a crucial role in European politics and diplomacy, leaving a deep mark on the history of both philosophy and mathematics. In philosophy, Leibniz is best remembered for his optimism, believing that our universe is the best possible universe that God could have created. Regarding time, Leibniz argued that time, like space, is entirely relative, possessing no independent existence. Space is the order of possibilities that can coexist, while time is the order of possibilities that can succeed one another, yet are related. This presents a complex problem: how to explain the dual nature of time, both sequential and continuous, both distinct and encompassing the moments that form it. In short, time is not one but two, both an objective, overarching natural law and a subjective human concept. Interestingly, only humans perceive time in such a profound way. We are the only species aware of our own mortality and the continuous passage of time. Where there are humans, there is time in the sense of conscious perception. Philosophy, through centuries, has helped us realize that time isn't just numbers on a clock, but an inseparable part of human consciousness and experience. This view also shares striking similarities with Buddhism. When discussing time and the universe, the Buddha often taught that with limited knowledge and a mind still full of delusions, humans cannot fully comprehend the origin of the universe. We can only understand generally that the formation and destruction of worlds occur over various long periods. More importantly, the Buddha advised his disciples not to seek the past or crave the future. The present moment is the most miraculous and meaningful. Living in the present is a way of life that wise individuals have experienced and passed down to future generations. By dwelling in the present, one realizes the oneness between oneself and others, and between oneself and all phenomena, directly perceiving that the ego is merely a distant, faint shadow, and one's existence is always dependent on the existence of others and countless other conditions. This isn't just a philosophy of life, but also a way to control time from within, by mastering one's own mind and perception. 2. Time travel through the lens of physics, a scientific dream. If philosophy gives us a deep insight into the nature of time, then physics is the path for us to materialize our dream of controlling it, especially the dream of time travel. Our modern understanding of time and causality largely stems from Einstein's theory of general relativity. Over a century ago, Einstein combined space and time into a unified entity, creating the concept of space-time, explaining the mechanics of both in an incredibly complex and elegant way. General relativity has been experimentally verified with extremely high precision, leading physicists to believe it is the key to accurately describing the causal structure of the universe. For decades, scientists have tried to use general relativity to analyze whether time travel is feasible. Some equations they've derived show that time travel is entirely compatible with relativity. However, physics must be grounded in mathematics. These equations would be meaningless if they didn't correspond to reality. So what is time travel? Simply put, it's the concept of moving a person or object from one point in time to another, similar to moving between different points in space. This movement can occur from the present backward to the past, or forward to the future. Although a familiar concept in philosophy and science fiction, it also receives some support from theoretical physics, often involving quantum mechanics, string theory, or wormholes. Frankly, traveling to the future seems much easier than traveling to the past. There's no general consensus on which ancient literary work represents the first example of time travel, as some only contain vague elements. However, in Hindu mythology, the epic Mahabharata mentions the story of King Kakudmi, who traveled to Brahma's realm and was shocked upon returning to Earth to find that thousands of years had passed. This is one of the earliest suggestions of future time travel. Currently, there are three most common theoretical methods for time travel to the future. 1. Cryosleep. This is the simplest way putting oneself into a state of near dormancy, then waiting for technology to advance and waking up in a future world. In fact, some people are currently undergoing cryosleep with the hope of being revived when science is advanced enough. However, as we discussed in the philosophy section, this isn't true time travel, as time still passes for the individual. It's merely a way to skip time. 2. Traveling at extremely high velocities. According to Einstein's special theory of relativity, when you move at velocities close to the speed of light, time will pass more slowly for you compared to those on Earth. This means you'll age less. Did you know that even when traveling between continents by plane, we are time traveling, albeit with an extremely tiny difference, only in nanoseconds? Imagine a spaceship flying so fast that in just a few years, thousands of years have passed on Earth. This is a real possibility based on verified physics. 3. Approaching a black hole's event horizon. The immense gravitational pull near a black hole causes time to bend and slow down significantly. In the famous movie Interstellar, the explorers spent only a few hours on a planet near a black hole, but upon returning, they found that 23 years had passed on Earth. While this is a cinematic example, the underlying physical principle is real. So what's the feasibility of each of these methods? Cryosleep, while the most feasible at present, isn't time travel in the literal sense. The third method, approaching a black hole, is far too unfeasible with our current technology. Thousands of years of scientific development have only brought us to the moon. How many more years will it take for someone to leave the solar system, let alone get close to a black hole? Therefore, we'll focus most on the second method, traveling at extremely high velocities. Imagine we have an experiment that needs a very, very long time to yield results, say 10,000 years. Assuming time travel technology exists, we would send that experiment on a spaceship, traveling close to the speed of light, then wait for it to return to Earth and retrieve the results. If this idea succeeded, it wouldn't just help us solve the problem of waiting for experiment results, but potentially all calculation problems, depending on the speed of the spaceship. However, there are significant difficulties with this approach. The biggest problem is the enormous energy required for acceleration. Currently, there's no technology to create a vehicle that can exceed the speed of light, because we haven't found a breakthrough beyond Einstein's legendary equation, E equals mc. This equation states that for an existing object, there's an interrelation between three quantities: energy, E, mass meter, and the speed of light, c. The mass of an object increases with its velocity, and an object at the speed of light would have infinite mass. For a spaceship to reach the speed of light, its mass would have to be half that of the Earth. We certainly can't build something like that. To accelerate a massive object to the speed of light, we would need an infinite energy source, which we currently have no way of achieving. Only massless particles like photons, light particles, can reach the speed of light. Anything with mass can only approach the speed of light. So is there a solution? One ambitious direction is to create negative energy matter. Still following E equals mc, to create negative energy matter, its mass would have to be negative, since the speed of light is always a positive constant. Quantum mechanics tells us that, in theory, it's possible to create negative energy matter in extremely small quantities and for extremely short durations. Furthermore, there's no evidence to suggest that we absolutely cannot create negative energy. Not only that, but we might find equations that allow time travel without needing these exotic materials. So this problem might just lie in our current technological state or our limited understanding of quantum mechanics. 3. Time paradoxes, troubles from the past. Traveling to the future sounds difficult and distant, but the most significant part must be this. Traveling back to the past is truly a difficult problem to solve, both in reality and in theory. If we view time as a linear flow according to Newton, time travel is essentially like a train running on a long track. As the flow of time passes, it leaves tracks behind. So is it possible to go backward along these tracks? This would simply be like opening the train door and jumping off, then walking backward along the track. But are you sure you wouldn't fall off the track? In reality, the time track here is invisible, intangible. You can feel it, but you can't precisely map it. So, if you jump off the time train, how would you know which way to go backward? It's very easy to stray from the track and fall into an infinite state. Even if you successfully return to the past, you might not be able to return to the present. How can you follow the time train if you're left behind? You run for 1 second, and the time train also runs for another second. Therefore, time travelers could get stuck in the past. But nothing is impossible. If the time travel device has enough speed to break the time barrier, everything changes entirely. However, the most interesting part of going back to the past lies here: the paradoxes that would arise. The most famous and difficult to resolve is the grandfather paradox. This is a problem that cannot be understood or solved. First described by science fiction author René Barjavel in Le Voyageur Imprudent, 1943. However, similar problems were described earlier, for example, Robert Heinlein's novel By His Bootstraps. Simply put, a man travels back in time and kills his grandfather before his grandfather marries his grandmother. As a result, his father would not be born, which means the man himself would never be born. So how could he have traveled back in time? But if he didn't go back in time to kill his grandfather, then his grandfather must be alive, which means he would be born and could travel back in time to kill his grandfather. These two situations negate the existence of both scenarios. This is a type of logical paradox. Although this theory is called the grandfather paradox, it doesn't exclusively refer to the impossibility of an individual being born. This concept includes any action that makes time travel to the past impossible from the outset. Another example is if we use scientific knowledge from scientist A to create a time machine, then use it to go back to the past and kill scientist A. If scientist A is killed before inventing that knowledge, then the time machine would never exist. And if it doesn't exist, how could we go back to the past to kill scientist A? A vicious cycle of causes and effects repeats itself. This leads us to the next paradox of going back to the past, the predestination paradox, also known as a causal loop. A causal loop in time involves event 1 occurring first as the cause, or at least one of the causes of event 2 occurring later. And through time travel, event 2 then becomes the cause of event 1. The paradox arises when the time traveler falls into a loop of predetermined events. For example, when someone goes back to the past to save someone from a car accident, and in the past, that person drives to the scene before the accident occurs, inadvertently hitting the very person they came back to save, causing the death that led their future self to want to go back in time. This theory is closely related to the ontological paradox in that something has no identifiable origin, in this case, the reason for the time travel itself. This paradox implies that time is immutable, and time travel remains a form of destiny, with event sequences unfolding due to causality rather than a supernatural origin. Similar to the predestination paradox, we have the bootstrap paradox or ontological paradox. This occurs when an object or piece of information from the future is sent to the past, affecting the existence of that information or object in the present without a clear origin. For example, you go back in time and hum a song by your favorite singer. Then, the singer hears it and writes that very song. So who created the song? Not you and not the singer. The bootstrap paradox always creates a mystery about the origin of information in many time travel novels and films. To make time travel a feasible endeavor, we must resolve these paradoxes. A common misconception in science fiction is that paradoxes can be created. Time travelers are often warned not to change too much of the past and not to repeat their past. Examples of this are found in many time travel films, such as the Back to the Future trilogy. Yet, in physics, a paradox is not an event that can actually happen, but rather a purely theoretical concept used to denote a contradiction within the theory itself. In other words, self-consistency paradoxes not only imply that time travel is a dangerous act, but also that it might be completely impossible. This is one of the motivations behind the chronology protection conjecture by theoretical physicist Stephen Hawking. Hawking believed that time travel was impossible. He even conducted a simple experiment to prove his point. He wrote an invitation detailing the location and time of a party he was hosting and sent it thousands of years into the future to invite future people to his party. Sending the letter was simple. Place the invitation in a sturdy metal box and bury it. Thousands of years later, future people would dig it up, know the party's location, and even his GPS coordinates on the timeline. If a time machine existed to travel back to the past, future people would surely come to Hawking's party. After all, he was a physicist with enough credibility for humanity. Sadly, Hawking waited all day, and no future people showed up to his party. 4. Solutions to paradoxes. Many timelines. These conjectures haven't been enough to convince other scientists. Instead of ruling out time travel because of paradoxes, we might be able to eliminate the paradoxes themselves, and the universe would be much more interesting. To resolve time travel paradoxes, theoretical physicist Igor Novikov proposed the Novikov self-consistency principle. The basic idea of this theory is that you can travel back to the past, but you cannot change the past. Novikov pointed out that if you went back 5 minutes and tried to destroy a clock, you would find it utterly impossible to do so. This is because the laws of physics would conspire to interfere and protect self-consistency from being violated. Applying this to Hawking's case, you could time travel to the past, but you couldn't change the past in any way. Even your appearance before Hawking at the party would be impossible. Physics always finds a way to maintain the consistency in history it has created. So if you could truly travel to the past, you might only exist there as an observer, like someone who only has view access in a Google Doc file, but no edit rights. But what's the benefit of time travel if you can't change the past? At the very least, it allows us to verify history. If you can't change history, then at least you know what truly happened and can check if what historians have recorded is accurate. However, even Novikov's self-consistency principle cannot fully resolve all paradoxes satisfactorily. Instead, one individual has proposed a more plausible theory, Barrett O'Neill. This theory describes time travel where there are multiple histories, and we can indeed change one of those histories. In other words, this idea is similar to what we see in Marvel movies, that multiple timelines exist simultaneously. This can resolve any time travel paradox, including the grandfather paradox. Solid states, when you exit a time machine, you will land in a different timeline, not your original one. In that timeline, you can do anything you want, including killing your grandfather, without changing anything in your original timeline. Because your grandfather in your primary timeline still lives, your father will still be born, and so will you. No paradox will occur here. For years, scientists have studied time travel paradoxes. Now, they are increasingly convinced that time travel is entirely possible, but only if our universe allows for the existence of multiple timelines. So the question is, can there be multiple timelines in the universe? From a quantum mechanics perspective, the answer seems to be yes. This is the many worlds interpretation, one of the accepted interpretations of quantum mechanics, which posits that every time a decision or a random event occurs, the universe splits into multiple parallel universes, each representing a possibility. Of course, even if they find such a theory, it won't be enough to prove that time travel is possible. But this at least means that time travel isn't completely ruled out by the self-consistency paradox. Time travel and parallel timelines always appear together in science fiction, but researchers have shown that they cannot be separated in the real world. General relativity and quantum mechanics tell us that time travel might be possible. And so, humanity has every right to dream, and even to seriously pursue the idea of building a time machine, a machine that jumps between different timelines and universes. You know, the present will eventually become the past. So we don't need to go back to the past to change that future. Let's change something right now so that in the future, you won't wish you had a time machine anymore. That's what truly means controlling time.